All right, now we're going to take a look at end behaviors of limits as well as limits of rational functions, um, which kind of starts branching off from our solving limits algebraically. So, end behaviors of limits are basically when the function approaches negative infinity and positive infinity. So, say we have um, like a parabola or something like this, and we're going to say as x approaches negative infinity, where would your y approach? Well, you know that in a parabola, the x will keep going, or the y will keep going up, keep going up. So as x approaches negative infinity, y would approach positive infinity. And as x approaches positive infinity, y will also approach positive infinity. That's basically what um, the end behavior of a polynomial is. And they'll start giving you harder and harder, maybe to the third, to the fourth, to the fifth, multiple terms, stuff like that. They always follow the highest degree term. Now, the reason why they follow the highest degree term, basically the one with the highest exponent, is say I have like x to the fifth minus x to the 4 minus 2x to the third plus 5x to the second, is because, okay, we start with 1, right? One's a pretty small number. They contribute pretty much evenly to it. But say we get to 1, like 10,000 or 100,000. 100,000 to the fifth power is going to be much bigger than any of these numbers. So as we start approaching infinity, or as we start approaching negative infinity, because to the fifth power out dwarfs everything else that's not the highest degree will always become insignificant at these larger values. So the end behavior, we will look at our highest degree term because all the other terms become insignificant. Now, let's do the example problem. So, what we have here is 2x to the third plus 4x minus 5. Which do we look at? Well, we look at the highest degree term, which is 2x to the third. Well, do we remember how x to the third um, looks? It looks something like this, right? So as it approaches negative infinity, so that's this way, negative infinity, your y value will also approach negative infinity. And just in case you forget how to do um, how like what the graph looks like, so say it's something like 2x to the 20th. How I imagine it is it'll either come out with a positive or negative number, right? And so say I plug in like 100. Well, 100 to the 20th power will be a positive number. That means as x gets larger, it'll always approach a positive number. So it's positive infinity. Okay, what about if I do negative 100? Well, because the exponent is an even number, I know it's always going to approach still a positive number. So I know this will also, even if it goes to negative infinity, it'll still approach positive infinity. And so if you forget how the graph looks or you don't know how the graph looks, just plug in a positive number, plug in a negative number, see where it would approach. So that's how you do it with limits of, or with uh, end behaviors of the highest degree term. Now let's look at limits of a rational function. Now, there's 3 rules. And for me, I think it's important to know why these rules happen. So this is for finding a horizontal asymptote, which is when there's a y value that the graph or that the function will never touch. And in order to find what the horizontal asymptote is, we compare the highest degree in the numerator to the highest degree in the denominator. So it'll just be like if I use a and b and then n and m, we are comparing n, we're comparing m. And when the highest degree in the numerator is larger than the denominator, so the top is larger than the bottom when it comes to these exponents, there's no horizontal asymptote. when it's smaller, there is a horizontal asymptote at 0. And when the highest degree is the same, we look at the coefficient of the numerator divided by the coefficient of the denominator. You can, that is great and dandy if you memorize all that, but here's how I think of it. Here's why this happens. So let's start with the first one. 5x to the third plus 3x plus 2 over 6x squared plus 2x plus 9. So remember when I said that everything as it approaches infinity or negative infinity, all of the smaller degrees start being insignificant. So when it's approaching positive infinity and negative infinity, they start becoming insignificant. So while I'm doing this calculation, I'm going to take these out because they're so insignificant at these higher numbers. So I'm only going to compare 5x to the third over 6x squared. Notice how we can simplify these to become 5x over 6. Well, now as x becomes a bit larger, notice how as x approaches infinity, this function will also approach infinity because nowhere is this going to stop, right? So say if it's 100, 1,000, 1,000,000, it'll keep going up. There's no limit. So that means there's no asymptote, right? Now, what if it was 5x squared over 6x to the third? So this is our second scenario, right? The denominator is larger than the numerator. We can still simplify it out. 5 over 6x. Now, as x approaches infinity, 5 over 6x, this would start approaching 0. Here's why. So we recognize that the denominator, as the denominator gets larger, the number itself gets smaller, yes. So if x is infinitely large, then the resulting value will be 0, right? It'll get infinitely small. So if we plug in 100, it'll be pretty small. Plug in 1,000, it'll get smaller. Plug in 1,000,000, it'll get so small that it reaches 0, pretty much. Next, when it's the same concept, right? 5x squared over 6x squared, we cancel these out. So that means the limit as x approaches infinity, because we cancel these out, it would just be 5 over 6. And that would be our answer. That would be your asymptote. So that's why these rules work. Now let's solve this. Let's take out all the unnecessary stuff. We get 5 over 4x. We can simplify it. And this would just be 0 because the denominator will be so insignificant. That makes sense? This one, 7x to the third over 4x to the third. These cancel out. Your answer is just 7 over 4. Right? That makes sense. Perfect. That's all for this lesson.